Okay, so we determined that there is a difference in a function, delta V. Delta V is the difference in the electric potential, and that's equal to minus the integral of the electric field over some length, over some line. We can write this as V, let's say we are using a radial coordinate r, so V of r minus V of some r naught is equal to minus E integral, minus the integral of E dot dr. And let's say that we want, well, first of all, let's decide that we have some freedom here in this function. Let's decide that if r naught equals infinity, then we have V of r naught is equal to 0. So we define that V at an infinite value of r is equal to 0. And so what is V of r? So let's find V of r for some special cases. So let's say that we have a sphere that has, it's a spherical shell of radius capital R, and on this shell, on the surface of the sphere, we put a uniform surface charge density, sigma, and so we want to find what is the electric potential, right? So this is the thing we want to look for. We know from Gauss's law, right, so we can use Gauss's law to find the electric field inside and outside, and so E over some sphere. So if we want to find the electric field out here as at some R value that's greater than capital R, then Gauss's law reads E times 4 pi r squared. The left-hand side is equal to all the charge would be inside those Gaussian surfaces, so it's sigma times 4 pi capital R squared, right? Because the charge lives on the shell over epsilon naught, and so we get that the electric field for R bigger than capital R, greater than or equal to, is equal to sigma R squared over epsilon naught R squared, right? It comes from this, solving for E, and then we put the unit vector, R hat. And so what is the V of R? So it's going to be minus the integral from, okay, so we said from infinity to R. So it depends on where that R is. Is that R greater than big R or less than? So we have two cases. We can have a V of R outside the shell and a V of R inside the shell. So this becomes integral E dot dr, which gives us, we found the electric field. We'll put it into here, minus sigma capital R squared R hat over epsilon naught. There's a variable 1 over R squared, right? So we're from infinity to R. Really should say R prime somewhere here, but these aren't the same. But let's just leave it for simplicity. Dr. So it looks like that, and the answer is, so we had sigma capital R squared over epsilon naught R from infinity to R, which gives us, what does it give us? Sigma R squared over epsilon naught R, and this is for R greater than or equal to capital R. That's the electric potential outside the shell. And if we want the electric potential inside the shell, V of R is going to be, right, so minus infinity to R, well, minus infinity to R, well, we have of E dot dr, we have to integrate all the way into the shell, plus a term that involves from R to R little r, where R little r is now going to be inside of the shell. So this little r here is less than capital R, right? So we have two terms. We have to continue to integrate all the way to little r inside the shell. So we get the, well, we know the electric field is actually 0 inside the shell. Well, we only got the electric field outside, but if we do this calculation for the electric field inside, it's the same as this, The left-hand side is the same, but the right-hand side has 0 because there's no charge inside, right? So we end up with with this term, which is simply sigma r. Now we replace little r with big R over epsilon naught, and this is the electric potential for r less than big R.